Okay, in this video I'll be going over ripple counters, mod 10 ripple counters, synchronous counters, and we'll end up with looking at down counting counters. Okay, so first we want to just quickly see the overview of what a counter is. It responds to a single clock input. We'll see that we're going to be taking and chaining together JK flip-flops to create these counters. The outputs will follow a defined sequence, meaning they will, the JKs are in the toggle state, so they will flip between 0 and 1, 0 and 1, and the chain following them will push digits either to the left or to the right, and we'll see how that works in a minute. Common task, you can either count up or count down, or another way of thinking that would be to increment or decrement the count. Okay, so if we're at 0001, we can go to 0010 and count up, or we could go the opposite, excuse me, and count down. And then lastly, we'll see that you can actually use it for division of frequency. If we haven't talked about that already, we'll see how that works. All right, so some quick characteristics here. We're going to be dealing with typically a 3 or 4-bit counter. A 4-bit counter, based on what we know about number of bits, that it would give us the range from 000 through 1111 in binary, right? So that's probably familiar in terms of when we are trying to generate the number of possible inputs. The same thing is true here. The counter will, if it's 4 bits, you'll literally be able to take it up to 1111. All right, let's see what else here. Modulus, we'll talk about that. The decade counter, basically counting up to 10 and resetting itself. And we'll look at a 4-bit and an 8-bit counter again, and how that works. Up and down, synchronous, asynchronous, and presettable and self-stopping counters. Not so much in this video, but in the future videos we will look at that. All right, so well, 4-bit counter counting from 4 zeros up through, hopefully you'll agree that we're talking 4 ones. The modulus of a counter is the number of states it can cycle through, such as a decade counter has a modulus of 10 going through that. And a 4-bit counter would have a modulus of 4, mod 4 counter, because it's constructed using 4 flip-flops, and hopefully understand that modulus of 4 has nothing to do with using 4 flip-flops, so this is false. All right, let's look at the ripple counter. So if you look at this, you see that you have JK flip-flops that are tied together. The output of the Q is going to the input of the clock. And at next flip-flop, the output of the Q goes into the input of the next clock, and so on. And what we're doing is we're looking at the output of Q. Say these could be your binary outputs, be tied to, in our case, in our labs, would be LEDs. And we would actually display those values. So the first output of the flip-flop is what we're going to consider the ones. This would be 2s, this would be 4s, this would be 8s. All right. The other thing to note here is that our JKs, the inputs JKs, are all equal to 1. So if they're equal to 1, that gives us, hopefully everyone recognizes, a toggle state in our flip-flop. Also, the presets and clears are set to 1. Seeing that these are active low inputs, when we set them to 1, they become inactive and we're not using them in any way. So we have a clock pulse coming through here. When that clock pulse comes through, it will literally toggle this flip-flop, which at that point will come into here and toggle this flip-flop, and so on. So let's see how that looks. Okay, we start off with 0, 0. And we're in toggle mode. Okay, so we give 1 pulse through there. So that first pulse comes through and puts out a 1 here. Well, that 1 now is sitting here, right? So this thing, on the negative transition, it's sitting at a 1. On the next pulse, and when this thing changes to a 0, you'll toggle this flip-flop. Second pulse comes in, it toggles this one. This guy goes to a 0. Now this guy's gone to the 1. Next input. So again, this guy is flipping between a 0 and a 1. This one is flipping between a 0 and 1. This one will go to a 0 and a 1. And it's literally, if you're following the binary output, it's counting in binary, right? So right now we're at a binary 5, and we do a pulse and we go to a 6, and we do another pulse and we go to a 7, and then in this next pulse, this guy's sitting at a 1, this guy's sitting at a 1, this guy's sitting at a 1. On the next pulse, this will go to a 0, output will go to 0. So it's going to toggle this one because this is going to a 0. That acts on the negative edge. This one will be going to 0. It's going to toggle on this one. And this last one here is sitting at a 1, and this will go to a 0. So now it'll kick out and toggle this from a 0 to a 1. Here we go. Boom. And there we go. So that's the ripple counter. So they all, if you're looking at this in terms of time, you can actually literally see that they all aren't going at the same time. Obviously, when we get to a synchronous counter, that would not be the case. They would all change at the same time. All right. Let's look at the waveforms of this. Here we go. All right. First one in, there's our clock pulse. So at this point here, the output, when we toggle the clock, our output's going high. So the next clock pulse, okay, we've got the clock pulse in. This output is going to change on the trailing edge of that clock pulse. So our output of Q1 now goes low. Well, when the output of Q1 goes low, that's the input of this guy, it's going to force this flip-flop high. Okay, that's what we have going on here. So now we have high sitting out here. Okay, we toggle again. We're going to get another clock pulse through. And there's the clock pulse. So the clock pulse is going to be pushed through this flip-flop, pushed through this flip-flop. Now it's sitting high right now. Okay, so the first flip-flop has transitioned back high. The second flip-flop remains high. It's not going to transition until this flip-flop goes low. Remember, all these flip-flops are acting on the negative trailing edge of that pulse. Okay, so next clock pulse comes through the negative edge. This guy's going to go. Negative edge here is going to toggle this guy to go. And on that negative edge here, our next flip-flop, the last one, is actually going to, or excuse me, not the last one, but the third one is actually now going to go high. So if you notice this, you're going to have a clock pulse. The first flip-flop is going to have a period twice as long as your clock pulse. Your next flip-flop is going to have a period that's twice as long as the first flip-flop, or 4 times as long as this one. And this one obviously would be twice as long as this one, or 8 times as long as this one. So you can see how the frequency here is actually being divided as we go through this. So if this was, say, 8 kilohertz, this would be 4 kilohertz, this would be 2 kilohertz, and this could be 1 kilohertz. So it's, again, frequency division. All right, going through a quiz. First pulse going in. After the first pulse, the counter will be a binary what? We got our first pulse coming in. It'll be a binary 1, right? Okay, let's look at the second question here if you want. Pause it, read it, see if you can answer that. Alright, what are we going to get here? After the second pulse, you have a binary 2, right? Third pulse. Oh, excuse me, after pulse 8, what do we get? Of a mod 16 counter will be a binary what? After 8 pulses. It's a binary 8, right? So for every pulse coming in, you're counting up 1. So when we had 1 pulse, we had an output of binary 1. We had 2 pulses, we had a binary 2. Now we have 8 pulses, we have a binary 8. After 15 pulses of the output of a mod 16 counter will be 15 pulses will be a binary 15, which is 4 ones. Alright, next, let's look at a decade counter. So this is a decade counter is really Similar to what we saw with the ripple counter, but instead of counting up to all the way to 15, this will stop at 9 and then reset. So what we have here is they've added in this NAND gate here. You have to remember, the NAND gate's always going to be 1 out. You have an output of 1 unless your two inputs are 1. So when your two inputs are 1, you're going to put out a 0, and when you put a 0 out, it's going to go into this is the clears. Okay, presets are 1s, your J and Ks are 1s, but your clears are tied to the output of this NAND gate. And think about it, when you put a 0 to a clear, which is active low, think about what it's going to do. A 0 on your clear, which is active low, means you're going to put out a 0 on your Qs. So basically, when we get a 1 here, output of second flip-flop, and we get a 1 on the first flip or last flip-flop, we're going to put out a 0, and we're going to clear all the flip-flops. So we'll go from whatever we had to 0, 0, 0, and we'll start over again. So let's go see how this works. All right. First pulse in, right? Okay. We've got a first pulse in 0, 0. Why do we have? Okay, let's back up. Okay, the initial count here was basically 0, 1, 1, 1, which is what, 7, right? So on the next count, on the next clock pulse, we went to 8. All right, so and then on the next clock pulse, so when we have an 8, we have a 1 here, but since this one's still at 0, we're not going to clear it yet. So our next clock pulse is going to take us to 9, right? So we still have a 1 here, but we still have a 0 here. We're looking for this 1 here, which will reset this whole thing. So we're at binary 9 right now. Then on the next clock pulse, we're going to get 1, 0, 1, 0, which that 1 here and that 1 here is going to reset this and set our JK flip-flops to a clear state and put out a 1. So here we go. Clock pulse in. Okay. It happens so quick that you don't actually recognize it, but basically you actually counted to 10 initially, and then this thing reset everything and went back to 0. So if we continue to count, we're just going to continue to start at 1 and work our way up again. Okay, 1, binary 2. Okay, so our 6th clock pulse is we're at 3 here. We continue to count up. All right. Is this a mod 10 or mod 16 counter? Well, remember, the mod 16 counter didn't have any additional circuitry to stop it. It literally would count all the way through to 15, whereas this mod 10, just we saw in the previous example, has the additional circuitry which is going to clear this once you hit 10. So this would be a mod 10. This circuit can be described as a decade or a 4-bit up counter. Okay. It does have 4 bits, but it is not a 4-bit counter. It would be considered a decade counter since it basically only counts up to 10 and, excuse me, counts up to 9 and then recycles. The gate generates a very low pulse when the count reaches 1, 0, 1, 0 and resets the counter to 0, 0, 0. The blank gate generates. Okay, so obviously the NAND gate here we're talking about, right? So after this, the counting sequence would be, is this true or false? So after this is a binary 6, the counting sequence would be, this is a 7, this is an 8, this is a 9, that's correct, this is a 10, and then at 10 it should go to 0. So in this case they're saying, does it go to binary 11? No. So this would be, hopefully you recognize this as being false. This would be a true 4-bit counter. It would take you up here and recycle back. But what we have is with this additional circuitry, this thing would reset when you get 1010. All right, and the last thing I want to cover is the down counter. If you look at this, hopefully you'll pick up, instead of coming out of Q and going into the clock, you come out of Q prime. So what you'll see now, instead of counting up, you're actually going to be counting down. That's the difference. So when you look at a counter sequence, you want to check the flip-flops, and if it's coming out of Q and going into a clock, you're going to be counting up. If you're coming out of Q prime and going into a clock, you're counting down. And again, all JKs are set at 1. All clears and presets are 1, so the only thing that's really driving this is the clock input and then the Q output. But if you notice, we're still displaying the Qs, although we're driving with the Q knots here. All right. So if we just talked about instead of Qs. Okay, so we're going to start with 111 because we want to count down. We'll start at the highest value and count down. So on the first clock pulse, this thing's going to toggle, right? So we're going to get a 0 out on the first clock pulse. Second clock pulse, this will toggle again. So this is going to go to a 1, and the next one's going to toggle, and it's going to go to a 0. And on the next clock pulse, this guy will toggle again. When this goes to 0, this is going to now sit at a 0, but this one's not going to toggle. We'll see when we look at the waveforms, but remember, this is only going to toggle every other change in state if it's this one. Okay, so there we go. We changed that. We changed this one, and then this one changed. And again, if you notice, we're counting down. Went from 3 to 2. Let's go back and make sure you saw the counting down sequence there. Okay, we started off at 7. We count down 1. We go to, that's a 6. We count down again. It goes to 5. Count down again, it goes to 4, then a 3, and then a 2. So it is counting down. And the key, again, to recognize this is it is coming off of your Q knots here. This circuit can be described as a 3-bit ripple. And hopefully after that discussion, recognize this as down counter. The circuit itself is a self-stopping 3-bit down counter, true or false. Is it a self-stopping? Or is it once it gets to 0, 0, it's going to roll over again? Well, we didn't in any way stop it, so it would roll over again. Self-stopping means once it got to 0, it would stop. And in this case, we haven't done anything to the circuitry to stop it at 0, 0. Okay, the counting sequence for the circuit, again, looking at this, you go from 7 to 6 to 5 to 4 to 3 to 2 to 1 to 0, 0 to all 1s again, 7, and then continue counting, right? So this would be true. We are counting down, and we are going to recirculate and start over again. Self-stopping down counter, this is really going to be a topic for the next video, so we'll pause this here, and that should do it.